cyclotron chamber. And this, ooh, okay. So it looks, in practice, somewhat like this. This isn't mine. This is a slightly higher-end cyclotron than what would be easy to build on a budget. So you have your magnet poles like this. The cyclotron fits in there, radially symmetric. Basically, you need the magnetic field to conform to the system's resonant frequency as there. So those quantities are fixed, has to apply to there. Or conversely, if you have a fixed magnetic field, you have to adjust L and C. So the frequency is given. And I'm actually running out of time, which is unfortunate. So there are guides for, I'm going to be posting on the wiki a guide for magnet construction, but one of the nice things also is that every month or two, these magnets and their power supplies show up on eBay for a few $100s, which is amazing. Or if you're connected to a research lab in any way, or a larger university, they sometimes appear out of the blue, and then you can get them and take them, and they're just amazing. So troubleshooting these magnets, if you're building one yourself, can be very tricky, so I'd recommend finding a way to scrounge one of them. So now, I guess I'm going to turn it over to questions at this point. I hope this was fairly clear. So, yes?
I guess I'll speak from here. What you described basically, Michael used the microphone.
Lovely.
Thank you. What you described is a system that is pretty low power. It's just in the mega electron volt range, and it smashes particles into a target, which you also know what it's made from and all that. What can this be used for today?
Well, something that could produce particles of these energies would be useful mostly for teaching. It would be something that you would build for a local school or build in conjunction with, like for a university-level physics lab, something like that, like a teaching lab. It would also be useful if you want a low-level radiation source for, well, I've always wanted to use mine for biology experiments, just irradiating different plants and seeing what would happen to them. But so you could use them for that. Basically, if you want to irradiate anything with ions, this is what you'd use it for. Any other questions? Yep.
Yeah, thank you. I was wondering, you were talking about using a square wave for the accelerating of the particles, but you also thought you could also use a sine wave. But if it's a resonating system with a high Q factor, why would you use a square wave at all? Because the system is oscillating at that frequency, so you only get the base frequency, I would think.
That's true. It really doesn't make a difference, actually. Like, it is possible to use the square wave because it's, you have the positive and negative of the square wave when the particles are just crossing that gap, and so so that's purely for the acceleration there. So there really isn't any benefit to using a square wave over a sine wave, but no drawback either. It's basically just with the square wave, you have the higher electric field constantly while they're traveling across the gap. So it's not, they're just constantly accelerating, or rather the derivative of the acceleration is constant. So the derivative of the acceleration doesn't go like this. I think, yes, that's true. Yep.
Just to clarify, you have used non-relativistic equations for the design. Are the energies really non-relativistic, or anything will change if you go to higher energies?
Well, for the protons at these energies, you don't need to incorporate relativistic equations. For electrons, it does become relevant. I think for this type of magnetic field, you get, I forget what beta is actually, but Yeah, I'm not going to guess. I'll be completely wrong if I guess what beta is. But for electrons, certainly you do need to incorporate relativistic effects.
Does the design still work when you go to relativistic energy?
Oh, it still works. It's just, well, if you expect classical results, you'd be wrong. So, but it's still, the design is still fine. Though if you're going up to relativistic energies, you need to be more careful with your shielding for the Bremsstrahlung effects that I mentioned earlier. But the design still holds. Yep.
How big is the whole thing?
Well, the cyclotron chamber itself is about 20 centimeters across and about 4 centimeters high, but it's the magnet and the magnet power supply that are very large. So the magnet itself, at least the one that I was using, was about a meter cube. The power supply was about half of that size. Magnet itself weighed about 300 pounds, too. It was a beast. But the whole system could comfortably fit in a footprint of about 1 meter by 2 meters.
Yes. What type of RF amplifier do you need?
Pardon?
What type of RF amplifier do you need? The RF amplifier for generating the sine wave and at high power levels. What type of amplifier do you need?
Oh, what type of amplifier? You don't need a special, just the sort of off-the-shelf amplifier that you'd use for other experiments. Like, you don't need it to go up to a high voltage. You can do this at, 50 volts.
What voltage does it put out? I thought it would run at several kilovolts. So you cannot use a regular RF amplifier for several kilovolts.
Well, you don't need, it doesn't need to be a very high voltage. Basically, if you have your magnetic field high enough, the spiral is tight enough so it can even encounter a small voltage like 50 volts, 100 volts, even 20 volts, something like that, enough times so it can go fairly fast. So it doesn't need to be any amplifier that you need to bring up to a very high voltage.
Okay, so you compensate with having a strong magnet.
Yeah.
Okay, thank you.
How do you define where the beam comes out? I mean, you have the magnetic field and the spiraling particles.
I'm sorry, what?
How do you define where the beam comes out of the cyclotron? You have the spiraling particles and you have the magnetic field, and as long as the magnetic field gets a hold of the particle, it will spiral. But where's the point where it's coming out?
Well, in the design that I showed you here, the particles don't exit the machine, they just impinge on the Faraday cup. So if you want the particles to actually exit, you'd need to make another port that was tangent to the outside of the spiral. And so just basically when they spiral out to that radius, they would encounter that tangential port, they could travel through that port and hit the piece of lithium, the piece of boron, beryllium that you have as your target. Or, well, yeah. Whatever else you want to be your target.
How much did it cost you, all in all?
Well, for mine, I was able to use a lot of surplus university equipment. So I ended up using, I think it was $500, $600 US of my advisor's money. So. But that was using a surplus magnet, hand-me-down function generator, amplifier, used vacuum pump, all of those things. Oh no, I bought the vacuum pump. That was $200, but.
Where do you get the network analyzer? Hold on.
That was my advisor's network analyzer. I didn't have to buy that.
The question was, where do you get the network analyzer? Because those things are quite expensive, right?
Those are, but that's when it's useful to be, to find one from a friend that you can borrow or already have one. The network analyzer, that is one of the sticky parts.
And how far is the network analyzer really necessary? Can you actually wing it with an open source design like the LC meter that only requires one verified capacitor, and then you can derive any L or C connected to it?
It is something that you could wing with. I guess you could wing it with a scope, for example, but it's.
It's just a lot more fun. with a
Yeah,
network
it's
analyzer.
nice. It's nice to have if you can get your hands on one. I mean, and you probably I'm sure everyone here knows someone who has a network analyzer. So just make friends with them. Bring your cyclotron bits over there. So, well.
Okay, in the back. Hold on.
I'm not sure I missed part, but what is the frequency that you're working at? Are we talking megahertz, gigahertz?
The frequency is on the order of megahertz. Mine was 15 megahertz. Okay. They, though an early design was tuned down to 8 megahertz, so in that range.
Any more? Any more?
Maybe I missed this, but what energy were you able to achieve, or were you able to measure the energy of your test cyclotron?
2 MeV.
Okay, and how did you verify that?
That actually, that's a good question. I tried to do some verification by putting in a lithium target in place of the Faraday cup and checking what happened to that. Yeah, the verification for that is tricky. It's 2 MeV calculated, so.
Okay, thanks.
You got me.
I mean, we got a few more minutes, so if you have any questions,
seriously?
shoot.
I had a schedule.
So you said there's a sort of trade-off. You can get away with a low